So last time we introduced the idea of an inner product. And let me just remind you what that is. An inner product for some vector space V is a map that takes two inputs, both from the vector space V, and spits out some scalar in whatever your field is. For us, we're going to restrict our attention to the field being either the reals or the complex numbers. So it's some map that satisfies the following properties. First off, if you're just working over the reals, it commutes but if you're working over the complex numbers, then you need to take the complex conjugate when you commute. So it's not quite commutative over the complex numbers. Second, it's linear in the second term. So V plus V inner product with some scalar times x plus y is going to just be that scalar times the inner product of Vx plus the inner product of Vy. And these two properties together then give you that, well, if you're working over the reals, because it's commutative, you also get that it's linear in the first term. That Cx plus y inner product with W would be the same as C inner product xw plus the inner product of yw. But if you're working over the complex numbers, this C becomes the complex conjugate, right? So we talked about that last time. So it's almost linear over C. Over C we say, almost bilinear. It's almost linear in both arguments. Over the real it is linear in both arguments. So over the reals, it's bilinear. Over the complex numbers, it's like 1.5 linear. It's linear in the first one, and almost linear in the second, argument, and almost linear in the first argument. So we call it sesquilinear, which is the Latin prefix meaning 1.5. And finally, it's positive definite, meaning that if you take the inner product of anything with itself, it should come out to be a non-negative value. And you'll have it equal to 0 exactly when V is the 0 vector. And so let me just say a comment about this one very briefly. If V is a vector in some vector space over the complex numbers, then the inner product of V and V is some complex number. And you might worry, if it's a complex number, what does it mean for a complex number to be greater than or equal to 0? Right? But then we go back and we think, and we're like, oh, wait a second. It's not just any old complex number. Because of the first property, you'll have to have that the inner product of V with itself is equal to the complex conjugate of the inner product of V with itself. And what kind of numbers are equal to the complex conjugates? Real numbers, right? When the imaginary part is 0. If the imaginary part's non-zero, you would change the plus bi to minus bi, and it would be different. So you'd only have an a plus bi be equal to a minus bi. You'd only have a complex number equal to its complex conjugate if the imaginary part is 0. Hence, this guy's always a real number, even if you're working over the complex numbers. If you're working over C, this might be a complex number if you have different V and W, but if you're doing the inner product of V with itself, it'll always come out to be a real number, right? So that's what the first property guarantees, and that's why I can say it's greater than or equal to 0. If it's just an arbitrary complex number, it's like, what do we mean that's greater than or equal to 0? is I greater than or equal to 0, right? We don't have necessarily a well-defined ordering like that on the complex numbers. Okay, great. This is also the reason I shake my attention to R or C. There are other fields that one might think about, and one might worry, like, what does it mean to be greater than or equal to 0 in some other field? But in R, it makes sense, and because in C, we have this conjugate property that forces it to be real, this last property makes sense over the reals and complex numbers. And any vector space we're thinking about in this class is going to be over R or C anyway. So, you know, in other classes, if you do some abstract algebra or whatever, you learn about other kinds of fields, and you can then think about, does this definition make sense if you're working over some other kind of field? Okay, that's good. Inner product. So what I want to do today is think specifically about this last property, because it's like, what's the game we're playing? Inner product is generalizing our notion of dot product. And in your first course in linear algebra, dot product was a way for you to figure out the length of a vector. And we can now do the exact same thing. What we're going to do today is I want to introduce a notion of norm, where the norm of a vector is just going to be defined to be the square root of that vector's inner product with itself. So if you have a vector space and you've picked some inner product on that vector space, we can now talk about the norm of the vector by just taking the inner product with itself and taking its square root. Exactly what you do in linear algebra with dot product. You say, in linear algebra, you say the norm of a vector squared, the length of a vector squared, is that vector dot itself, right? Okay, so let me just remark a few properties of, well, let me give you an example. Let me give you an example. Example. So if we're working over Rn, then we can choose as our inner product the dot product. So we'll have Rn with the dot product. This is what I was just saying. Then we have the familiar norm, the length of some vector. So if you have some vector, you can, I guess, write this as like a v1 down through vn. And we would just be saying that the length of your vector is the square root of v dotted with itself, which just comes out to be the square root of v1 squared up through vn squared, right? Familiar notion of length of a vector, the magnitude of a vector. Here I'm calling it the norm of the vector. But this now generalizes to any vector space. So say you're working over continuous functions. We can say these are continuous functions over the interval AB. Then it's like, how do you find the magnitude or the norm of a continuous function? Well, pick a inner product on the vector space, and the one we introduced last time was the inner product that just integrates the product of your functions over that space. So for us, the norm of a vector is really the norm of, what is a vector here? A vector is a function. The norm of your function will just be the square root of taking the definite integral from a to b of f of x times itself, f of x times f of x, so f of x squared dx. And now you can go and calculate the norms of whatever function you want, as long as they belong to, say, this vector space of continuous functions over the interval AB, where we're thinking about inner product as being defined by this guy. There are other inner products you could define over that space. There are other inner products you could define over Rn. So our notion of norm will be dependent upon our choice for inner product. Okay. But since we have some notion of length, then we can start introducing familiar language from linear algebra. For example, I can introduce the notion of a unit vector. It's just going to be a vector of length 1, right? So if I'm given some vector v, then what I can do is I can take V divided by its magnitude, and you're like, well, what's the magnitude of this guy now? Well, it should be just 1. Let's check that. Let me call this U. What is the length, what is the magnitude of U? It's like, well, let's check. This should come out to be the square root of the inner product of U with itself. What's the inner product of U with itself? Well, that's the same thing as the inner product of V divided by the magnitude of V with V divided by the magnitude of V. And now we want to use some properties of the inner product. Any inner product satisfies these properties. In particular, it's linear in the second argument, so you can pull constants out. And in the first, it's linear in the second argument. It's almost linear in the first argument, except you take the complex conjugate of that constant. Although if the constant's real, you can just pull it out. What do we have here? Well, these are real constants. Right, we just had this discussion. The norm comes out to be some real length, and so you can just pull this out. So you get the square root of 1 over the norm of V squared times the inner product of V with itself. And the inner product of V with itself will just be the norm squared, so this is just the square root of 1, so it's just 1. That's saying this works just like you think it should. If you take any vector and you divide it by its norm, you get a vector whose norm is now 1. So we have unit vectors. Okay, what are other kinds of things that you do in linear algebra with magnitude? Like, what are some of the observations you make once you introduce this idea of the magnitude or the length or the norm of a vector? What are some things you say about it? Well, let's just think back to linear algebra really fast. One of the things you have is if you have two vectors in Rn, vectors v and w, we mentioned this briefly last week, you can think of the angle between them, right? And we have this relationship that v dot w is equal to cosine of the angle between them times magnitude of v, magnitude of w, right? And this relationship bridges to two other ideas. One is this notion of what it means for two vectors to be orthogonal, where we can say being orthogonal means the angle between them is pi over 2, meaning the angle between them is 0, so their dot product should be 0. So we have some connection between being orthogonal, and the dot product coming out to be 0. We'll return to that in a moment. Can we define a similar notion? If the inner product is 0, then our vectors are orthogonal. We'll do that in a second. But this also gives rise to a very important inequality. Cosine is always between -1 and 1. Therefore, the absolute value of this guy on the left will always be strictly less than or equal to the product of the magnitudes of v and w. And this is called Cauchy-Schwarz, right? This is an important inequality that I think you talked about quite a bit in your first course linear algebra, and comes up a number of other places, is mathematics as well. So this is the Cauchy-Schwarz inequality. Right, the absolute value of the guy on the left will be, well, since this absolute value of this will be somewhere between 0 and 1, hence it's less than or equal to the product of the magnitudes. So we want to prove that a similar thing holds now in arbitrary vector spaces. All we're doing today is lifting our results from linear algebra, saying that now we've defined some analogy to the dot product, all of these results also generalize. That's what we're trying to do today. So here's my generalized Cauchy-Schwarz theorem. It's that if you're given some v in W in a vector space V that has some inner product, we want to say that the inner product of V and W, okay, what kind of creature is this? Well, it's a scalar, but it's a scalar in your field, which could be a real number or it could be a complex number. So if I want to say something about taking the absolute value of this and it being less than the magnitude of V and the magnitude of W, like, let's think a second. What do I mean by taking the absolute value of a complex number? Because it could be complex, right? So let's just remind ourselves. What would I mean if this was like a complex number and I'm taking the absolute value of some A plus BI? Just the magnitude. So this is literally just the square root of A plus BI times A minus BI, or that is just the square root of A squared plus B squared. So we mean the same thing here, right? If you're working over the real numbers, you don't have to worry about that, just a real number. But because we might be working over the complex numbers, we need to remind ourselves what this means. There are other results we have too, right? In your first course on linear algebra, right? Like if you have some vector V and you add to it some vector W, you get the vector V plus W, right? And like there's a relationship between the length of these vectors. What's that relationship? Well, they make a triangle. So when you add up V and W, it better not be more than the length of V plus W. Right? So we also have the triangle inequality. We also have the triangle inequality, which just states that for any V and W in your vector space, the magnitude of V plus W should be bounded above by the magnitude of V plus the magnitude of W. Like this is immediately obvious when you're working on Rn. I mean, just geometry, it's a triangle, right? So like in Rn, you prove this, but it's like totally believable. It's not totally obvious that you're working in any vector space now over R or C with whatever, norm you want, like this norm, right? Like this is not obvious. Right? Like you should think like what is this saying? This is saying, here's a nice application of this, right? An application of this is saying that if you take two continuous functions f and g that are continuous functions, then you have the square root of the integral of f of x plus g of x squared dx from a to b is less than or equal to the square root of the integral from a to b of f of x dx f of x squared dx plus the square root of the integral from a to b of g of x squared dx. Right? Like, I don't think that's obvious. You can think about it, and you can prove this. You can just prove this particular case, but we're proving something much stronger. That whenever you have an inner product, like this inner product, or whichever one you're working with, these kinds of relations will hold. Like this does not just follow from drawing a picture of a triangle and be like, it's a triangle. It's like, you can expand this, you can think about the definition of integration. It's not too hard to show this, but these are the kinds of things that this is really saying, right? Okay. So I don't want to prove both of these today. So what I'm going to do is I'm going to just take Cauchy-Schwarz for granted. There's a full proof in the text. You can read the full proof. but I want to show how the triangle inequality is a corollary of it, right? So let's take this, refer to the text if you want the full proof, and instead I want to prove the triangle inequality because I want to save time to survey a few more results. We're just trying to see everything that generalizes from linear algebra to arbitrary vector spaces. Okay, so it's like, how are we going to do this? And it's like, well, we go back. Our norm is defined to be a square root of an inner product. And so a natural first move is let's begin with one side, like say v plus w. And what we're going to do is we're going to square it. Because now it's just the inner product of v plus w with v plus w. And now we can use our properties of the inner product. It's linear in the second argument. So this is going to be the inner product of v plus w with v plus the inner product of v plus w with w. And then, well, it's almost linear in the first, but if you had some c out front, it comes out as the complex. But there's no c's out front we have to worry about. The coefficients here are 1. They'll come out as just the complex conjugate of 1, which is still just 1. So effectively, it's linear in the first argument as well for us. That is, we can write this as the inner product of v and v plus the inner product of w and v plus, and now to the second guy, the inner product of v and w plus the inner product of w and w. Careful, you want to combine these, but the inner product isn't quite commutative. If we want to commute this first guy, we don't get the inner product of v and w, we get its complex conjugate. So let's take a second to think. If this guy becomes a complex conjugate, it's like you're adding a minus bi with a plus bi. What does that sum come out to be? Great, 2 times a. That is, when you add these, the sum's going to come out to be, you still have the first term, inner product of v and v, but the sum of these is just 2 times whatever the real part is of this complex number v inner product w. It's your 2a, right? 2a, where a is the real part of the complex number, plus w. Okay, now let's think. The inner product of v with itself is just the magnitude of v squared. The inner product of w with itself is just the magnitude of w squared. 2 times the real part. It's like 2 times a. Okay? How can we, what can we do with that? And at some point we want to use Cauchy-Schwarz. It's like, well over here the magnitude of v with w is the square root of a squared plus b squared, right? And that is something that's definitely going to be just as large as a. Because if b is 0, that becomes a. Otherwise, it's larger than a. That is, this term right here, 2 times the real part, 2 times your a, will be bounded above by the magnitude of v inner product with w. It's bounded above by that. And there's 2 of them. Don't forget the times 2 piece, times 2. 2 times the real part. 2 times a is bounded above by 2 times the square root of a squared plus b squared. But now we use Cauchy-Schwarz. And Cauchy-Schwarz tells us that we have v magnitude of v squared plus 2 times, this is bounded above by the magnitude of v times the magnitude of w plus the magnitude of w squared, which is exactly the magnitude of v plus the magnitude of w squared. So we recover our inequality. We happy so far? Let me just make one more comment. Actually, Cauchy-Schwarz says something a little bit stronger. When do you have equality here? Just thinking back to the case of Rn. When do you have equality between these? Well, you'd want your cosine to be either 1 or negative 1, which means you want your vectors to either be pointing in the same direction or in opposite directions, right? So this happens, you have equality here, exactly when your v and your w are collinear. They're either pointing in the same direction or opposite directions. How do we generalize the idea of collinear? In general, what does it mean for two vectors to be collinear? I mean, these could be functions, these could be matrices. Doesn't really mean like, what do we mean by collinear, right? What does it mean for two to be collinear? Good, one could be a scalar multiple of the other, or one of them could be 0, I guess, which would still be a scalar multiple of the other. So one is a scalar multiple of the other, like v is some constant times w, or maybe w is 0 and c is just whatever. Okay, and if one is a scalar multiple of the other, that's the same thing as saying they're linearly dependent. So we have equality exactly when your v and w are linearly dependent. Let's come down here and see how the triangle inequality works. When do you get equality in the triangle inequality? Well, back here in the case of Rn, it's a similar story where it's like if your v and your w are pointing in the same direction, or collinear, then you should get equality. Let's check, does that happen? Well, as we go through the proof, where did the inequalities come from? There was one inequality here that came from the fact that this real part, in general, your a, your real part, is less than or equal to this guy, which was the square root of a squared plus b squared. When are we going to get equality here? We'll get equality when the b is 0. What does it mean for b to be 0? Well, let's go up. That's saying that this guy is a real value. This is going to be equality. You're going to have equality when your v and w is real. The inner product of v with w is real. So like, okay, when is that going to happen? Well, there's one more condition we can think about. We have a second inequality. This inequality comes from the Cauchy-Schwarz, which we said this one will only give you equality when your v and w are linearly dependent. That is, one is a scalar multiple of the other. One could be 0, but one's a scalar multiple of the other. Let's put those two conditions together. So V is a scalar multiple of W, or W is a scalar multiple of V. But let's just assume that V is a scalar multiple of W. And let's come down here now and ask what's going to have to take place so that the inner product of V with C times V, some scalar multiple of V, comes out to be real. Well, this is just going to equal C times the inner product of V with itself. We already know the inner product of V with itself has to be real. So what does this tell you about C? Well, C has to be real, right? From this first condition, that they're linearly dependent, you have the possibility that C is just some element of your field. It could be a complex number. But down here we're saying, no, actually, in order for this to come out to be real, which you need in order to have equality here, your C can't be complex. You have to have that your C is a real number. So it's not just that one is a scalar copy of the other, where it could be a complex scalar copy. It's that one of them is a real scalar copy of the other. And so that's only going to happen if V is a real scalar copy of W, or W is a real scalar copy of V. That is, if V is some CW, or W is some copy of CV, where C is a real number. That's the only time you get equality. That is, really, V and W be pointing in the same direction. One is a real scalar copy of the other, even though you may be working in a field where V can be a complex copy of W. If it's a complex copy, you won't necessarily have equality. Right? Equality is only going to come if one's a real scalar copy of the other. Okay. So if you're working over the real numbers, there's nothing like really complex here. It's just when we're working over the complex numbers, it's important to note it's a little bit stronger than saying they're linearly dependent, because these could be linearly dependent where one is a complex scalar copy of the other. For equality to hold in the triangle inequality, you need one to be a real scalar copy of the other. Okay. Probably spend too much time. Very small point, but it's worth noting. Okay. Trying to extend everything we can from linear algebra. We've done like Cauchy-Schwarz and triangle inequality. Let's come to this one now, orthogonal. Let's just extend the notion of orthogonal to any vector space. Right? So here's my definition. We say V and W in some vector space are orthogonal if the inverse product of V with W is 0. Careful. Let's think of an example. Suppose you have your vector space as P1. Linear equations, right? Polynomials of degree up to 1. Right? Then we could define an inner product as a dot product. Given two guys in here, like we could define given some f and g, let's say f and g are some functions. I don't want to keep writing given. F and g are something in P1. We could define the inner product of f with g just to be the dot product of writing f and G as two-dimensional vectors, over your basis B. Right? So this P1 has some basis. A nice basis for it is like 1x. So if you have some linear polynomial a plus bx, you can write that as a vector over the basis B as just the vector AB. Right? So whatever your two polynomials are, they're just dimension 2 vectors, and you can just dot them like regular. And so this is one fine way to define inner product. You just define the inner product as a dot product. Or you can do something more creative. You could say something like, let's say the inner product between f and g is this other one we saw before. We can say it's the integral from wherever to wherever, let's say 0 to 1, of f of x times g of x dx. Two different ways to define the inner product. Okay, give me two vectors, that is two polynomials, that are orthogonal under the first definition. Well, it's like, well, maybe the guys that correspond to 1, 0, and 0, 1. So what two vectors would that be? Yeah, anything of the form just a constant, anything of the form a constant times x. In particular, we could have like 1 and x. Because then it's like you just write what is the vector that corresponds to 1? Well, that's the vector 1, 0. What's the vector that corresponds to x? That's the vector 0, 1. So that comes out to be 0. Right? So 1 and x are orthogonal. Let's look down here. Under the second definition, what is the inner product between 1 and x? Let's do it. You want to integrate from 0 to 1, the multiple of these two functions. 1 times x is x dx. So the antiderivative of x is 1/2 x squared. You plug in 1/2 x squared. We're going to plug in 0 and 1. It comes out to be 1/2. 1 and x are not orthogonal under this inner product. Right? Okay. So being orthogonal is dependent upon your choice of inner product. If you choose a different inner product, different vectors may or may not be orthogonal. That's all I'm trying to say right now. So this depends on your choice of inner product. In general, I'm going to introduce the language of an inner product space, where an inner product space, instead of saying a vector space, I'm going to say inner product space, where I just mean you have some choice of vector space plus and you've committed to a particular inner product. So it's like, in this inner product space, in this inner product space, P1 with the dot product as the inner product, 1 and x are orthogonal. In this inner product space, P1, where inner product is defined by finding the definite integral, 1 and x are not orthogonal. So same vector space with different inner products can change if two vectors are orthogonal or not. So we always need to be clear what our choice of inner product is. Okay, great. That said, if you've committed to some vector space, you've committed to some inner product, what I want to say is being orthogonal behaves like it does in Rn. In particular, if you have orthogonal vectors, they all point in different directions. That is, orthogonal vectors are linearly independent. That's not obvious from our definition, but let's prove it really fast. So if we're given, so here's a nice little property, a little proposition. If we're given some collection of vectors, say v1 through Vn inside some vector space. And I want these to be non-zero vectors. It's like, sure, I mean, one way you get orthogonality is just to pick one of these to be 0, and, well, then they're going to be linearly dependent because 0 is linearly dependent with anything. But if you pick two linearly independent vectors, then they're like, you know, right angle to each other. So if I pick two non-zero vectors such that the inner product of any two of them, the inner product of any vi with vj is 0 for any I not equal to j, then what I want to say is I want to say that this collection v1 through vn are linearly independent. So if you can get them to be orthogonal to each other and they're non-zero, that's enough to guarantee linear independence. So how do we show a collection of vectors linearly independent? We say, well, suppose you can find some linear combination of them that adds up to the 0 vector. Then I want to show that all those constants are 0. Let's first show that the first constant is 0, and then the same kind of argument will work for any of them. Note, what is V1's inner product with 0? We haven't said this explicitly. What should it be? What should be the inner product of anything with 0? 0. I don't know if we said it explicitly. Where does this come from? Well, you could get it from the original definition by properties of linearity, or you could come look at Cauchy-Schwarz and you're like, well, it has to be bound by 0. So what's something whose magnitude is bound by 0? Only 0, right? Lots of ways you can see this. But this inner product has to be 0. Right? Inner product of anything with 0 is 0. But we just said 0 is the same thing as the linear combination of C1 V1 through Cn Vn. What do we do now? Well, when you see something like this, you're like, let's take advantage of the fact that the inner product is linear in the second argument. So that's the same thing as C1. Oh, this should be a V1. V1. This is the same thing as C1 times the inner product of V1 with V1 plus C2 times the inner product of V1 with V2 all the way through Cn times the inner product of C1 with Vn. But we've said that your V1 through Vn are mutually orthogonal. So the inner product of V1 of anything else is just 0. These are all just 0. Those are all 0. So you're just left with C1 times the inner product of V1 with itself. But we're picking non-zero vectors. So this inner product of a non-zero vector with itself must be non-zero. Hence, since C1 times it is 0, we must conclude that your C1 is 0. And similarly, just instead of doing the inner product of V1, you could do V2 or V3 up to Vn. You get that your C2 up through your Cn are all 0. Hence, your V1 through your Vn are linearly independent. Okay. I think maybe last time someone asked this question of like, how do you like pick this definition of inner product? You know, how do we know how to generalize the notion of dot product? And the answer is you generalize it in such a way that all these proofs work. right? Like, you think like, what properties do we need to get these proofs to work? And you notice we just keep using the 3 properties that we picked. And so it's like, we generalize in such a way that all the nice properties of dot product extend to arbitrary vector spaces. So we now have, if you have a collection of orthogonal vectors, they're linearly independent. So like, what is this like suggesting? What's being screamed at you right now? If we can find orthogonal guys, they're linearly independent. Oh, if we can find enough of them, we can get a basis. A basis where all the vectors are orthogonal, right? And then in linear algebra, it's like, oh, it's really nice not just when they're all orthogonal, but also when they're all unit. And we have a notion of unit that we talked about before. So now we can say we've recovered a notion of an orthonormal basis, right? So we say B, which is some collection V1 through Vn, is an orthonormal basis for some vector space V if, like if what? Well, 2 properties. 1, the inner product of any Vi with any Vj should be 0 for I not equal to j, and the inner product of anything with itself should be 1. Okay, I'm tempted to squeeze in a lot more, but like you probably know where the story's going at this point. It's like we have an orthonormal basis. What do we want? We want some procedure that gives us a way to build an orthonormal basis. If I have a basis that's not orthonormal, how do I turn it into an orthonormal basis? And what's that procedure called? Gram-Schmidt. And so what we'll do next time is I'll just briefly mention that, oh yeah, that procedure called Gram-Schmidt, you can do it still. And so we'll justify that briefly, and then we'll have that, we'll conclude that since every finite dimensional vector space has a basis, that in fact every finite dimensional vector space has an orthonormal basis, right? And therefore we recover that there's this really nice structure to vector spaces in general, not the same kind of structure that we have in Rn. Okay, so that's what we'll wrap up with the next time, and then move on to talking about some corollaries of that.